Right, good evening, Lamai. We are a bit late today. Okay, let's start the class. Right. Okay, today we are going to discuss about the period trends. Right, you guys can clearly hear me, right? Right. Chris, are you okay with the stuff? You can clearly hear me now, so just put a message to the chat box. So Nation is also there. Right, that's right. Okay, let's start the class. Right, today we are going to discuss about the period trends. Before going to the period trends, right, we'll first discuss about a bit about the period table, right? So period trends appears in the period table, right? Okay, two scientists were involved in constructing the period table, right? The model period table, right? Those are the Dmitry Mendeleev and the Lothar Meyer, right? So those things are there at the page number 13, right? So just go to that, right? I'll quickly discuss about the stuff appearing there, right? Before going to the period trends, right? So the Lothar Meyer and the Dmitry Mendeleev are the two scientists, right, who discovered the period table or who constructed the period table, right? Okay, so that is first point. You should have to mention. We have to mention with the period table, right? Then we should know that the elements in your period table is ordered in the order of increasing atomic number, right? That is the second thing we need to mention here. In the period table, the elements are ordered in the increasing order of atomic number, right? Okay, right. Next, right? Let's discuss a bit about the period table. What are the blocks available with the period table, right? Okay, so when it comes to period table, right, you will see, right, this kind of a stuff, right? So this is the normal period table, right? So in most of the diagrams, the period table could be seen like this, right? So the hydrogen and helium normally situated like this. So in a period table, right, we could see some few blocks are appearing, right, like this. Okay, so this is referred to as the S block. S block. When your final electrons are filled to S subshells, right, those elements are actually categorized under the S block, right? We call that like sodium, lithium, right? Those guys, potassium, rubidium, right? Then it comes the beryllium, magnesium, calcium, strontium, barium, right? For those guys, the final electron is filled to a S subshell, so that those elements are categorized under the S block. That is why they are referred to as S block elements, right? So we have the P block here in your period table. You have the P block here, right? Under the P block, you can see the elements which actually are with the valence electron, the final electron with the P subshell. If you fill the last electron to a P subshell, right, such elements are categorized under P block, right? So you have the P block there. So between the S and P blocks, there are two blocks are appearing, right? One is D block, right? The other one is the F block, right? Same criteria is followed to when right, giving the elements to the D and F block as well, right? So if the ultimate electron is filled to a D subshell, then such elements are categorized under D block, and when the ultimate electron is filled to a F subshell, those are categorized under the F block. So we have 4 blocks in our modern period table, right? And you can see that those things are appearing, right? Here, this D block is referred to as the transition elements, or the block with the transition elements, and F block is considered as the block with the inner transition elements, right? Actually, when it comes to F block, right, it is actually it's kind of this, Lamai. So actually this S, D and P blocks are at the same plane. So if you are thinking of a 2D diagram of the periodic table, you can see the S, D and P blocks. But when it comes to F block, those elements are actually right inside the plane, right? It's like so if you have a plane like this, right, like this, if the SPD blocks appearing at this plane, right, then the D block elements are appearing like this, right? The D block elements are appearing like this. So it comes to 3D diagram of a period table, you can clearly show the F block elements, right? So S, P, D block elements are like this. If so those are like this, the F block elements are appearing like this. So that is why those are referred to as inner transition elements. The transition elements are the elements which bridge the S and P blocks. The transition between S and P is provided by the D block elements. That is why we call the elements in D block as transition elements, right? The F block elements are referred to as inner transition elements because the F block elements, right, reside, right, actually inside the D block elements, right? So that is kind of an idea, right? So when it comes to 3D period table, you can clearly see those things, right? So this is our modern period table, right? So this is actually constructed according to in the order of increasing atomic number, increasing proton number. They have ordered the elements to the SP and D blocks here, right? So that is all about the period table, right? Some ideas about the period table. And then when it comes to period table, we should know about two other things, right? In period table, right, these are the columns. These columns, we have 18 columns like that, right? In period table, we have 18 columns like that, right? You can clearly see 18 columns are appearing, 2 columns with the S block, 10 columns with the D block, and 6 columns with the P block, right? Those columns are referred to as groups. Those columns are referred to as groups. So in our period table, you have 18 groups. The first group and second group belongs to the S block. The third to 12th, those groups belongs to D block, and 13 to 18, those 6 groups belongs to P block. So altogether 18 groups are there in your period table, right? What are groups? The groups are the elements, right, in a column, right? Column of elements are referred to as groups, right? So then we have rows as well. So rows like this. So those are also given a name. These rows, right, left to right, the rows are named as periods. Rows are named as periods in period table. So such 7 periods are appearing. The first period, second period, third, fourth, fifth, sixth, 7. Altogether 7 periods are appearing with the period table, right? So period of elements, right? Second row elements, second period of elements, third period of elements, fourth period of elements, like that, right? So the rows are named as periods, right? So columns are named as groups in your period table, and the rows are named as periods, right? We have 18 columns, that means 18 groups, and 7 rows, that means 7 periods in our period table, right? So when it comes to these columns and rows, or the groups and periods, we can see some common trends are appearing, right? When it comes to groups, right? So their outer electronic configuration is same. So when it comes to first group, their outer electronic configuration would be looks like this: NS1, always 1 electron at the S subshell for the first group. When it comes to second group, the outer electronic configuration would be looks like NS2, right? So the outer electronic configurations of group of elements actually coming up with a common trend. So if you are to think of 13th group, its outer electronic configuration would look like, right, NS2 NP1, right, like that. So when it comes to column of elements, group of elements, their outer electronic configurations comes with a common trend, right? So that when it comes to group of elements, right, we can say the final valence electronic structure is same, so that the chemical properties are same, right? Chemical properties arise That means the bonding things arise due to the outer electronic structure. So when it comes to groups of elements, right? So as their outer electronic structure is the same, normally the group of elements will show kind of similar chemical properties, right? So that is what we need to know about group of elements. About those group of elements, right, we will discuss further things with the unit 6. We have a unit 6, right? They are also in organic chemistry, unit 6. They are also will study thoroughly about the periodic table, right? They are we mainly concerned about the trends appearing with group of elements. The trends appearing with the first group element, trends appearing with the second group elements, like that. We will discuss about the trends appearing of with group of elements at the unit 6, right? But in unit 1 here, we are mainly focusing into the trends appearing with the periods along a period, right? What will happen when going towards right of a period? That is what we are going to study with the unit 1, right? So that is why we call this section as the periodic trends in S and P block elements. The periodic trends, basically today onwards, right, we are going to discuss about the periodic trends, the trends appearing when going towards left to right of a period, right? That is our main focus with this part. This is actually the final section of the unit 1, right? So thoroughly we will discuss about the periodic trends here, right? Not about the trends with the groups, but about the trends with the periods when going towards left to right, right? That is our main focus here, right? Okay, when it comes to periodic trends, we are to learn about 6 such periodic trends. 6 such periodic trends, right? If you are to write a note that one by one, those are like this, right? We'll discuss one by one, right? First of all, I'll write the 6 period trends we are going to study under this topic, right? Main topic, right? So first we are going to study about the, right? Well, first we are going to study about the effective nuclear charge, right? Effective nuclear charge. Then we'll study about the atomic radius under period trends. Then we will study about the ionic radius, then about the, right, ionization age. So you may have heard about the ionization energy trend in your O levels as well. You have learnt about the ionization energy trend. Do you remember that zigzag trend, zigzag pattern with the ionization energies going towards right of a period, right? The zigzag trend, right? The ionization energy. We will thoroughly follow about that trend, right? And we'll come up with the reasons about that trend as well, right? Then number 5, right? We'll discuss about right, electron gain energy, right? Electron gain energy, and ultimately we'll discuss about the electronegativity. So those are the 6 period trends we are to follow, right, under this main topic, the period trends under S and P block elements, right? Today I am trying to complete these 3 sections. That is our main focus today. Let's try, right, to complete the 3 sections today, right? So we'll start the period trends from now onwards. Before that, I need to say something, Lamai. So I thought of starting the second lesson, right? With the new month, right? We are heading up to a new month, right? So at the next class, right, I thought of starting the second lesson, the bonding lesson, right? Today we will cover these 3 period trends, right? So in the next class, right, we start the unit 2, the bonding lesson, right? Drawing Lewis structures and the stuff will be discussed, right, in the next class, right? So when the things goes on, we'll one by one discuss about these trends as well. Only these 3 things to study, so we can come up with 1.5 lessons would be enough to complete these 3 things, right? So we'll complete those things gradually, but before that we'll start the unit 2, right? So while doing the unit 2, we'll discuss about these topics one by one, right? So is it okay? I think no worries with that. No, Chris, Deshana, are you okay with that? Right? No worries, no? Right, I won't hear you today that much, right? Anyway, right.
Now only the mic was not on, sir. Now it's on actually.
Okay, okay.
Now it's okay.
Right.
That's why we couldn't speak to you.
Okay, right. So you can clearly hear me, no? Right, that's okay. Right, okay. Right, right. So we'll start, today we'll try to complete these three, and next day we'll start the unit 2. Then gradually we'll discuss about these things as well, one by one, right? Okay, right. So we'll start with the, what? Effective nuclear charge as the first period trend, right? Okay, let's start with that. Let's come up with the first period trend, right? Effective nuclear charge, right? That is the first discussion for today, right? Effective nuclear charge. Right, let's discuss. The idea is this. Basically, so when it comes to chemical properties, right, those chemical properties are mainly decided. Those chemical properties are mainly decided by the valence electrons, right? So basically, let's think of atom. So if you are to think of an atom, right, you have the nucleus, right? I'll write it in a different color, right? So you have the nucleus, right? Right, so you have electrons, right? I'll write just few electrons, right? So you have electrons here. So when it comes to electrons, basically we are of major two types of electrons, right? Major two types of electrons, right? Which are referred to as inner electrons and valence shell electrons, right? In an atom, normally we have inner electrons and valence shell electrons, right? You may have more of those electrons, inner electrons, right? So these are referred to as inner electrons, and the electrons at the outermost shell, right, are referred to as valence electrons. So in an atom, you have inner electrons and valence electrons, right? For the chemical activity, for the chemical properties, right, the most important kind of electrons are actually the valence electrons, right? Actually, the valence electrons, the outermost electrons, are the ones which participate in bonding, right? So when it comes to chemical properties, the bonding and the stuff, right? Chemistry is always the valence shell of electrons, outermost shell of electrons. The bonds form, the bonds break, all the things happens with the outermost electrons, right? So the chemical properties are basically, right, on the outermost electrons, behaves with the outermost electrons. So most important kind of electrons are at the outermost shell of your any considering atom, right? So basically these chemical reactivity and the chemical properties are, right, really varying according to how much these electrons are attracted to the nucleus, how much these outer electrons are attracted to the nucleus. So if the outer electrons are greatly attracted, it is hard to release the electrons, so that it is hard to ionize your atoms, right? So you see, when forming sodium chloride kind of a stuff, right? So first you need to come up with the sodium ions, sodium positive ions, right? For that you need to release some outer electrons. You need to release one of the outer electrons, right? So if you are to come up with the magnesium chloride, right, with a reaction, right, you need to come up with the magnesium 2 plus ion. That means you need to release two of outermost electrons, right? The electrons are released from the outermost subshell, right? So basically the outermost electrons are the ones which are more important, and when it comes to chemical reactivity, they are attracting strength to the nucleus matters, right? If the electrons are greatly attracted to the nucleus, right, that the reactivity may vary according to that. It is hard to produce the positive ions if the electrons are greatly attracted. If the electrons are loosely attracted, it is easy to produce the positive ions. So that will vary, the reactivity will vary. If you think of like this, so if you need to come up with some other idea, it's like this, no? So let's see. So if you have to think of the sodium's reactivity with water, if you think of sodium's reactivity with water, you know what will happen. The sodium will form the sodium hydroxide, right, and H2 with water. If you think of magnesium with water, right, magnesium will form the magnesium hydroxide, right, magnesium hydroxide plus H2, right. These are two reactions, but you know, right, even with the cold water, this reaction happens vigorously. Even with the cold water, this thing happens, right? But when it comes to magnesium's reaction with cold water, it is not happening. To do that reaction, we need some heat to provide. So chemical reactivity of this thing is low. The reactivity, when it comes to reactivity, the reactivity of this thing is high, and the reactivity of this thing is low. We need some hot water. We need to right, heat the water. So as the reactivity is low, to increase the reactivity, we need to increase the temperature. So you may have heard about the reactivity as well, no? So reaction rates, right? To increase the reaction rate, we need to supply some heat, temperature. Then only this reaction will occur. If not, the reaction won't occur. So that means the chemical reactivity is better with this one, but very less with this one, right? Okay, so you see with the same compound, the two kind of elements are showing two kind of reactivities, right? So let's discuss about that thing. Actually, that is all because of this factor, right? Actually, the effective charge plays a big role in considering the reactivity of the sodium and magnesium, right? At the end of this lesson, at the end of this part, you will clearly understood why the sodium is more reactive and magnesium is less reactive. So if you have to note that, you can clearly see the sodium produces sodium plus ion here with the OH minus. Here the magnesium produces magnesium 2 plus ion with the 2 of OH minuses, right? So producing Na plus from the sodium is easier than producing Mg2 plus from the magnesium. We'll see why is that. So those things could be clearly understood with the concepts of the effective charge, right? That is why we are learning these kind of things. Basically, all the chemical properties of the elements are actually, right, depending on the how much the valence electrons are attracted to the nucleus, right? So that is something, right, which will be affected the reactivity. We'll discuss that thing, right, with this effective charge concept, right? So right, ultimately at the end of the section, we'll come to these two reactions again, right? First, let's discuss about. Let's come to the discussion about the effective charge as again, right? Okay, so it is very clear the chemical reactivity is depending on how strong these electrons, the valence electrons, are attracted to the nucleus. Actually, when it comes to the attraction, of to the nucleus, right? Basically, we need to think of two things, right? This attraction or the attraction to the nucleus, right? Mainly because of this thing, right? The attraction to the nucleus, basically because of the opposite charges of the nucleus and the considering valence electron, right? This electron will be attracted to the nucleus, right? Due to the opposite charges appearing with the proton and the protons and the electrons, right? So this is the attraction. Actually, this is the nuclear attraction, right? But remember, due to the appearance of the inner electrons, this attraction will be, right, decreased. The attraction strength of this thing will be decreased due to the appearance of these repulsions by the inertial electrons, right? The inertial electrons will repel these electrons outwards, so that the attraction here, right, would become smaller. The net attraction, the effective attraction, the net attraction becomes smaller due to the, right, formation of inner electrons, as those will repel your outermost, considering valence electrons, those will repel from the nucleus, right? So not only the inertial electrons but also the valential electrons do the same kind of effect, right? Due to the appearance of the same shell electrons also, your considering electron, right, will be bit right, push away from the nucleus, right? So due to the appearance of inertial electrons and the onshell electrons, the attraction, the net attraction felt by the valence shell electron will be decreased, right? Because of the repulsions done by the inertial and the onshell electrons, the attracting power felt by this electron towards the nucleus will decrease, right? So that effective attracting power, that resultant attractive power towards this nucleus by this considering electron is referred to as the effective nuclear charge. That is what the effective nuclear charge means, right? The nuclear charge is the actual charge at the nucleus. The nuclear charge is the actual charge at the nucleus, which will be given by the number of protons in the nucleus. But the effective charge is the charge actually felt by the considering electron. The effective charge is the charge actually felt by the considering electron. That won't going to be the same as the nuclear charge, because due to the appearance of inertial and the onshell electrons, due to the appearance of those and the repulsions from those, the nuclear charge felt by this electron is decreased than the actual nuclear charge which is there at the nucleus. So the effective nuclear charge, which is the net or the resultant nuclear charge, right, felt by this electron is lesser than the actual nuclear charge then, right? So we could come up with the equation for that, right? So it's like this repulsion things, the repulsion strength, the repulsion property, right, that action is referred to as the shielding effect. The shielding effect, right? These repulsive forces appearing with the electrons, right, due to the proximity of inner and the onshell electrons are referred to as the shielding effect, right? So this is the repulsions due to, right, repulsions due to proximity of, right, or the closeness of co-electrons, proximity of the closeness of co-electrons, right? Co-electrons means the right, inner and, right, same shell electrons, right? That effect is referred to as the shielding effect, right? These repulsions, this effect is referred to as the shielding effect, right? The shielding effect, or one can say the screening effect. So these wordings carry some meaning, right? Shielding or the screening. Actually, these co-electrons, right? The co-electrons, the inertial and these ones will shield the nucleus for your considering electron. The inertial electrons and the onshell electrons will shield the nucleus from your, right, to your considering electron. Shield or screen. These guys will screen your nucleus, right, to your considering electron, right? So that is why the shielding or screening effect, that name is given. So, right, we can say like this. So the effective nuclear charge, if you have to think of the effective nuclear charge, is it effective? One can say this effective nuclear charge is equal to nuclear charge minus the shielding effect. Nuclear charge minus the shielding effect, right? This is the formula which gives you the effective nuclear charge. The effective charge is actually the charge felt by the considering electron, that is equal to the nuclear charge, which is the charge actually at your nucleus. The nuclear charge is the charge actually at your nucleus minus the shielding effect. The shielding effect will decrease the actual nuclear charge, right? So that some decreased charge will be felt by the considering electron, right? This is this idea in a formula, right? So this is the concept of effective nuclear charge, right? So again I am telling you, right, the concept of electronegative charge is this. Actually, the charge felt by a concerning electron, right, a charge felt by a valence electron is actually lesser than the charge in your nucleus. Why is that? Because some shielding effect is happening, right, occurring due to the proximity of inner shell and the your same shell electrons, which is known as the shielding effect, right? So that is the final idea here with the effective charge, right? Effective charge is what? Effective charge is actually the charge felt by the constraining electron. Actual charge felt by the constraining electron, right? This is the actual charge, but effective charge is the charge felt by the constraining electron, right? So that is all about the shielding effect. So Lamai, just draw this one. Just draw this picture at that space. So they are saying like that, right? In an atom that containing a number of electrons, right? An electron experience less attraction than it would if other electrons were not there. If other electrons were not there, this electron will be totally attracted to the nucleus. But when the other electrons are also there, some repulsions may occur, some shielding effect, some screening effect will be occurred, right? So that the actual nuclear charge felt by this one is lesser than the actual nuclear charge. The charge felt by this electron is lesser than the actual nuclear charge. That is what, right? We say with this equation, right? So just draw this picture now. Just draw this picture and put this formula as well, right? So I'll label few more stuff here, right? This is the valence electrons. These are the valence electrons, right? So these are the valence electrons, right? So you have here the inner electrons, inertial electrons, and same electrons, right? Electrons in same shell, right? These two types are referred to as co-electrons. Co-electrons, right? These two kinds are referred to as co-electrons, right? Right now. So just quickly draw this picture, Lamai. Quickly draw this picture, right? So I'll send you a picture as well. So till then you better start writing. So this is the concept of effective charge, right? Okay, we'll do some calculations with this equation as well, right? So let's label these stuff as well. Right? Let's label the stuff there as well, right? So this is effective charge. Right, this is nuclear charge. Actually, nuclear charge is actually number of protons there at the nucleus. And this is screening or the shielding effect. Right? So normally, Lamai, when it comes screening, right, the inner electrons contributes to 1 unit of shielding, while the on shell electrons contribute 0.35 units of shielding. We'll discuss about that thing, right? So more shielding will be done by the inner electrons. You can clearly see more repulsions. The greater repulsions will be done by the inertial electrons, slight repulsions are done by the same shell electrons, right? So the same shell or the on shell electrons, same on, right? Shell electrons, the shielding effect is lesser than the inner shell electrons, right? That is also should be noted, right? More repulsions will be done by the inner shell electrons. That is why their contribution is 1 unit, right? So the same shell electrons will participate in less repulsions, right? So their contribution in shielding is less than the inner shell electrons. Actually, both of these two guys are referred to as co-electrons. Remember that, right? Both of them are referred to as co-electrons, right? No? Co-electrons, right? Remember, when it comes to co-electrons, right? Same shell electrons are also calculated. Same shell electrons are also calculated when it comes to co-electrons, right? Not only the inner shell electrons. In this case, right? For shielding, not only the inner shell electrons, but also the same shell electrons are also participating for these kind of repulsions. Not only the inner shell electrons, but the same shell electrons are also contributing, right? Keep it that in mind, right? So when it comes to helium, I'll discuss about that. When it comes to helium, right? In helium also we have a shielding effect. In helium also we have a shielding effect, right? One may think that in your helium atom, as you don't have any inertial electrons, one may think that helium is not with a shielding effect. That is not the case. Even with helium, it is with some on shell electrons. So that with helium as well, you have a shielding effect. With helium as well, your effective charge is not equal to the nuclear charge, right? Are you clear with that idea? So I'll do that such a working if you need, right? So like this number, it goes to helium. See the concept. I'll calculate the effective charge for helium, right? Helium atom. Helium atom. See, when it comes to helium, right, you have +2 charge at the nucleus, that is your second atom, right? 2 protons there, right? So helium's electron structure is this now. At the n equals 1, you have 2 electrons. So that you clearly see there are no such inertial electrons. Let's consider about this electron. We are calculating the effective charge of this electron. We said EFF for this electron. Right? If you are calculating the effective charge of this electron, right? For this electron, you don't have any inertial electrons. No inertial electrons for this electron. But this electron contains some on shell electron. So some shielding is there, right? Some shielding is there. See, some shielding will be there, right? With the on shell electrons, that will repel, right? That will repel your electron from your nucleus, right? This thing will repel your electron from your nucleus, right? So you clearly see, right? Some shielding effect will be appearing. So if you are to calculate the shielding, calculate the effective charge of the helium, it would be like this. The effective charge of helium is actually Z minus S. Z is what? Z is number of protons. That is 2 plus 2. Number of protons. The actual nuclear charge appearing at the nucleus. That is Z. Minus S is what? S is the shielding effect. Here the shielding is done by only the on shell electrons. Shielding is done by only the on shell electrons. No, shielding is done by only the on shell electrons. This contribution is there. So only one on shell electron is there. So one can write 1 into 0.35 units of shielding. Only one on shell electron is there, right? We are considering the effective charge for this electron. So only one on shell electron is there. So the shielding is 1 into 0.35. So your thing looks like this. The ultimate number is 1 plus 1 65 plus 1.65, right? That is the effective nuclear charge, right, of a valence electron in helium. This is the effective charge of a valence electron in helium, right? Affinity charge of valence electron in helium. So you clearly see the affinity charge is less than the nuclear charge of the helium. Affinity charge is less than the nuclear charge of the helium, even though the inertial electrons are not appearing. Even though the inertial electrons are not appearing, affinity charge is less than the nuclear charge, right? So remember that not only the inertial electrons but also the same shell electrons are contributing the shielding, so that your affinity charge will be less than the nuclear charge if own shell electrons are appearing, right now. So that is the situation with the helium, right? So it is clear now. So that is how we are supposed to come up with a calculation, right, with the affinity charge, right? Deshana, Chris, are you clear with this concept of this calculation as well? Do you have any idea? Do you have any? Yeah, it's okay, no? Chris, what about this one? Are you clear with the calculation? No worries, no? Okay, so you can come to the you can put write your reviews with to the cat box as well, right? Okay, so that is how the affinity charge is calculated. So just write this stuff, Lamai. After writing this one, right? Just write the stuff here under this. No need to do this calculation. We'll do some of these kind of calculations further, right? So if you need, you can put this thing, or you can have a screen catch here. So under this thing, just write like this, right? I just write like this. This partially screened nuclear charge. This partially screened nuclear charge is termed as this partially screened nuclear charge is termed as red, write it in red color. The effective nuclear charge is termed as the effective nuclear charge. Put a comma and write ZEFF. Right? It's termed as the effective nuclear charge ZEFF. Right? Okay. At the next line, come to the normal color and write. At the next line, with the normal color, just write the effective nuclear charge. The effective nuclear charge within brackets, which is there with all the atoms, the effective nuclear charge within brackets, which is there with all the atoms. Come to the red color and write other than hydrogen. Close the brackets. Come to the normal color and write. Is always less than the actual nuclear charge. Is always less than the actual nuclear charge. Right? Is always less than the actual nuclear charge. Right? Is always less than the actual nuclear charge. So you see, if you need, now you can write this one. If you have some space, you can put this example, right? So even with the helium, the effective nuclear charge is less than the actual nuclear charge, right? This is the actual nuclear charge, right? This is the Z, right? This is the actual nuclear charge. Actual nuclear charge, right? This is the effective nuclear charge. So that value is less than the +2, right? If you need, you can write this stuff there. Right now, even with helium, right? the affinity charge is less than the actual nuclear charge, right? Because even in helium you have inertial electrons. If you have inertial electrons or inertial electrons, definitely your affinity charge will be a value lower than the actual nuclear charge, right? That is the idea, right now. Okay, right. Then write something about the shielding effect. Let's complete the note on shielding effect as well, right? Let's write about the shielding effect now, right? Shielding effect. Okay, let's write this stuff, Lama. We have discussed now. Just to complete the note, let's write these things about the shielding effect as well, right? Just write in normal color. Just write. Okay. For a considering electron, the shielding is due to the for a considering electron, the shielding is due to the write it in red color, come to red color and write co-electrons. Shielding is due to the co-electrons. Shielding is due to the co-electrons. Within brackets, just write inertial electrons and electrons in same shell. Inertial electrons and electrons in same shell. Those are the electrons referred to as co-electrons, right? Due to the co-electrons, within brackets, write inertial electrons and electrons in same shell. Close the brackets, right? Close the brackets and continue. Which are more closer to the nucleus? Right now, which are more closer to the nucleus? Right now, which are more closer to the nucleus? Right. Put a dash and write. Then put a dash. Come to the next line and put a dash and write. Greater the number of co-electrons, and higher the number of co-shells, greater the number of co-shells, higher the number of co-shells, CO, the co-shells. Write it in red color. Greater will be the shielding effect. Greater the number of co-electrons and higher the number of co-shells. Write it in red color. Greater will be the shielding effect. Right? The idea is clear, no? Right. Greater will be the shielding effect. Okay. Right. Let's do some calculations. On affinity charge. Right? Let's discuss what will happen to the affinity charge when going down a group and when going towards right of a period. Let's discuss about that thing. Right? Let's discuss what will happen to the affinity charge when going down a group, and most importantly when going towards right of a period, because we are discussing about this affinity charge under the periodic trends. We are discussing about the affinity charge, so that we should think of the trend there appearing when going towards right of a period. We should examine that, right? So that let's discuss a bit, or let's do some calculations, right, to come up with these values for the affinity charge going towards right of a period, right? When doing so, we'll do the same calculations for the going down the group as well, right? Okay, that is kind of a bonus, no? Right? Okay, let's come up with some calculations, right, to get that idea of affinity charge being a periodic trend. See, I'll do some calculations, right? I'll do a few of the calculations, and better you continue with me, right? Okay, let's do some calculations on affinity charge. Right. See. Okay. So we'll do some calculations, right? So first, you can come up with a clean A4 sheet. Just take a clean A4 sheet, or else you can use the back side of your tute, the last pages of a tute. You may have some free pages at the end of your tute, right? You can use the last page, the last blank page in your tute to do this calculation, right? So let's come up with such a kind of this kind of thing, right? So I'll so I need some space, right? So just come up with this kind of a table, right? We could come up with this kind of a table, right? So now we are supposed to calculate the affinity charge, right? So let's do kind of a calculation now. Right, so here the lithium, sodium, with this we expect to get the trend when going down a group, and then going to right, beryllium, boron, carbon, like that. Here also magnesium, right, aluminium, silicon, right, the calcium. I'll calculate the affinity charge of a few elements, and you can continue with me, right? So I'll do the first 2-3 calculations, right? So it comes to lithium. When it comes to lithium, it is carrying some right, 2-1 configuration, 2-1 configuration. The atom 2-1 is 11th, is 19, right? The atomic number. 4, 5, the atomic number 6, right? 12, 13, 14, like that. Atomic number 20, right? 2-1 looks like this, no? 2-1 means you have plus 3 at your nucleus, 2 electrons at the first shell, and 1 electron at the valence shell. This is how the 2-1 looks like, right? So I'm going to calculate the affinity charge for this electron. The nuclear charge felt by a valence electron. Let's do the calculation. Z EFF is equal to Z minus S. Z is plus 3, the nuclear charge plus 3, minus S. S is done by the inner electrons and the on shell electrons. You have 2 of inner electrons to this one. These 2 are inner electrons. 2 of inner electrons. So 2 into 1. Inner electron contribute with 1 unit. Such 2 electrons are there. 2 into 1. And you don't have any other on shell electrons. So that is 0. So the affinity charge is going to be plus 3 minus 2, that is plus 1. The affinity charge of lithium is plus 1. The nuclear charge is plus 3, the affinity charge is plus 1. Affinity charge is plus 1. See? Let's calculate the same thing with some other guys. Beryllium. See? This thing is Z minus S. Beryllium is what? Beryllium is it, right? 2-2 configuration, 2-2 configuration. That means you have +4 at the nucleus, you have 2 electrons here, you have one more electron than the considering electron at your valence shell. At your valence shell you have 2 electrons now. 2 electrons now. So this is your considering electron. This is for what we are referring to the affinity charge, and you have another own shell electron, right? So let's calculate the affinity charge. It's going to be, you have 4 protons there, +4, this it, minus shielding effect. So you have 2 co-electrons, 2 inner electrons, 2 into 1, 2 inner electrons plus 1 on shell electrons, 1 into 0.35, 1 into 0.35, 1 on shell electron, 1 into 0.35, 1 on shell electron carries 0.35 units of shielding. So this is going to be +4 minus is 2.35. So the affinity charge is going to be what? 1.65 plus 1.65 plus 1.65. See, right? So can you do the same for all the other elements appearing here? So I'll do for magnesium as well. Just see the magnesium's one as well. Then you can continue. The magnesium is carrying kind of electron configuration like 282. 282. That means you have 12 protons at your nucleus, then 2 electrons at the first shell, 8 electrons at the second shell, at the third shell. This is your considering electron. Other than that, 1 electron is appearing. Right? This is your considering electron. Other than that, 1 electron is appearing. So calculate the affinity charge. It will give you like ZEFF is Z minus S. The Z value is +12. Shielding effect, right? You have 10 inner electrons. You have 10 inner electrons. 2 into 8, 10 to this electron. These 10 are inner electrons. So 10 into 1. So inner electron contribute 1 unit to the shielding. Plus you have 1 on shell electron. So 1 into 0.35. 1 into 0.35. So that will give you some value like 12 plus 12 minus 10.35. So that will give you plus 1.65. Right? So like that, just calculate for all of these 10 elements. Right? Just do it by your own. Right? So I'll continue the stuff. I'll continue the calculation. So don't look at the board first of all. First do the calculation with your own. After that, you can check whether you have done correctly or not by looking at the board. Right? So I'll continue. You also just continue without looking at the board. Right? Okay. Do the calculations and then only we could see what will happen going towards right, what is the trend going towards right of a period, and what will be the trend going towards down a group. We can discuss about that thing only if we are to get these values, right? Let's do the calculations here, right? Okay, let's continue. For boron, it is going to be 2, 3, 2, 3. The 5 electrons are there. That means plus 5 at the nucleus and 2 electrons are at the inner shell, and other than the considering electron, another 2 electrons are there at your valence shell for the boron, right? So let's come up with the affinity charge, right? Z is effective is actually Z minus S right? So Z is plus 5 minus S means you have two electrons at a inertial plus, right, 2 electrons in own shells, 2 into 0.35, no? So you will come up with plus 5 minus 2.7. That will give you, right, that will give you plus 2.30. Let's do the same for the carbon as well. The carbon is 2, 4, so plus 6 there, and 2 electrons at the inner shell. Other than the considering electron, you have another 3 electrons at your own shell, right? Let's calculate the shielding effect for this electron. So if it may charge for that electron, Z minus S, Z is plus 6 as you have 6 protons at your nucleus, minus 2 into 1 plus 3 into 0.35. So it is going to be plus 6 minus, right, 2 and 3.05. That is actually, right, looks like plus 2.95, right now. That is about the carbons effective charge. So you can do for the other things as well. Let's do that stuff. Continue. This is 2, 8, 3 for 13. So plus 13 with 2 electrons, 8 electrons, and other than the considering, you have 2 electrons. So Z is, if it is Z minus S, Z is plus 13, S, you have 10 co-electrons, 10 inner electrons, right? 10 into 1 plus 2 of own shell electrons, so 2 and 3, 0.35. So that is looks like plus 13 minus 10.70, that is plus 2.3. For the silicon, let's do, right, that is 2, 8, 4. So that is your 14th atom, 2 electrons at the first level, 8 electrons at the second energy level, and other than the considering electron, you have 3 electrons at the last energy level. So the Z effective is Z minus S. Z is plus 14, the nuclear charge, minus S means number of electrons at the first of all, number of electrons at the inner shells, 10 into 1 plus, right, 0.35 units into 3. You have 3 outer shell electrons and own shell electrons, 0.35 into that. So it is going to be plus 14 minus, right, 10 and 11.05, right, 11.0. That is that will give you plus 2.95. Right, for these two as well, right. This is 281 plus 11, 2 electrons, 8 electrons, and just 1 electron here, Z effective is Z minus S. Z is plus 11 minus shielding fit 10 into 1 plus 0. So plus 11 minus 10 is plus 1. For the potassium, 2881 2 electrons, 8 electrons, 8 electrons and 1 electron. See, this is the considering electron. So infinity charge is Z minus S. Z is plus 19 minus S. You have 18 electrons as inner electrons, 18 into 1, and you have 0 electrons as own shell electrons, right? So plus 19 minus 18, that is plus 1. For the calcium, it is 2882. So if you consider it, right, plus 20, 2 means other than the considering electron you have only 1 electron. Other than the considering electron you have only 1 electron. 2 here. So EFF is Z minus S. So that is plus 20 minus plus 20 is the nuclear charge minus the shielding fit. You have 18 electrons at the inner shells, 18 to 1 plus 1 electron as a non-shell electron. 1 into 0.35, that will give you plus 20 minus 18.35, that is plus 1.765. Right? This is how the calculation is done. So, do you guys get these values? So I'll send you a picture as well. Right? Do the calculation, right, with your own, right? You can then you can think of the patterns here, right? So right now, right, I think you clearly see the numbers, right? Okay, numbers are clear right now. Okay, so numbers are okay. You can have a screen capture as well now. Just see. So I'll leave that. Just take a screen capture here. Right. So what patterns you can see when going through this? Please tell me. Right. What you can see when going down. When going down a group. Right, what kind of pattern you observe? Any idea, please? When going down? Same, no? When going down, the unit charge will be the same. See? So we can conclude that. We can say going down a group, if unit charge won't change. If unit charge won't change going down a group. Right? Going down a group, if unit charge won't change, right? What happens when going towards right? Do you see the trend? Do you see the trend, Chris? Going towards right. It increases, no? It increases. So starting with plus 1. So it is plus 1.65 plus 2.3 plus 2.95. So it is increasing by, right, 0.65 units, by 0.65 units, right? Going towards right, the effective charge is increasing by 0.65 units. See, right? So that is the trend. That is the period trend. That is the period trend. Going towards right of a period, your effective nuclear charge will increase by 0.65 units, right? So when going down a group, nothing happens to the effective nuclear charge. Effective nuclear charge won't change going down a group, but going towards right of a period, the effective charge will increase by 0.65 units, right? That is the major idea we are discussing here, right? So we have done a calculation and clearly we had seen the trend, right? So that is the most important stuff to gather here, right? Very clear now, right? Okay, so we'll write these things. We'll write these things in our note, right? So it is better to have this note, right, in a separate paper, right? So that you will clearly get the idea, right? Okay, let's write. You can complete the stuff now. After taking screenshot, you can complete the stuff, right? Okay, then we'll complete the note, right? You are okay with this thing, Chris, right? Do we need more time to complete this one? Chris, do you need any time to complete this one? Or are you okay? Right. Okay. Right. No. Right. Not hearing that much. I think it will be okay now. Right. So. Right. I'll send you a screen capture as well. Then it will be clear, right? Screen capture. Right. Right now. Okay. Then we'll continue. Right now. So you have a point there at the bottom of the note, right? From left to right across any period, that thing is there. From left to right across any period, just write this thing. First point, point number 1, right? There at the bottom space, right? You can write EZ, put a comma, nuclear charge, EZ, comma, nuclear charge. Just write it in red color. Increases. EZ increases. You see? Going towards right of a period, EZ increases, no? Plus 3, plus 4, plus 5, plus 6. EZ increases. No? Plus 11, plus 12, plus 13, plus 14. EZ increases, right? That is the first thing to observe here. EZ increases. Nuclear charge increases. Within brackets, you can write as number of protons increase. As number of protons increase. The atomic number increases means number of protons increase, right? This number of protons increase, right? Within brackets, just write as number of protons increase. That is the first point. That's what happens when going towards right of a period, right? Second point, just write S, comma, shielding effect. S, comma, shielding effect. Second point, right? S, comma, shielding effect. S, comma, shielding effect. Again come to the red color. And write slightly increases. You see the shielding effect here. Here the shielding effect is 2. Here it is 2.35. Here it is 2.70, 3.05. See, the number slightly increases going towards right. See, you clearly see that number increases by 0.35 units. Here 10, it is 10.35, and here 10.70, and here 11.05. The number increases at 0.35 units, slightly increases. That is due to the addition of a on shell electron. Here you have 0 on shell electrons, here you have 1 on shell electron, here you have 2 on shell electrons, here you have 3 other on shell electrons. So as increasement of the on shell electrons, the shielding effect will slightly increase by 0.35 units going towards right of a period. Right? Let's write that thing, no? The S, the shielding effect in red color, slightly increase. Slightly increase. Within brackets you can write the reason. Within brackets just write. As number of same shell electrons increase. 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 Close the brackets. Close the brackets. Right? Close the brackets. Right. That is the second point. That is what happens with the shielding effect. Earlier we had discussed what happens with the the nuclear charge. Then we had discussed about what happens with the shielding effect going towards right of a period. Right. Now let's come to the effective unit charge. ZEFF. Just right. Third point. ZEFF. Comma effective unit charge. ZEFF, comma effective unit charge. Effective unit charge. ZEFF, comma effective unit charge. Write it in red color. Increases. Effective unit charge increases. See what happens here? You start with 1 plus 1.65 plus 2.3 plus 2.9. Different charge increases. Actually increases by 0.65 units. Going towards right, it increases by 0.65 units. You clearly see that. Even see plus 1 and plus 1.65. Different charge increases by 0.65 units. The thing is this. The reason is this. See, the reason is actually the effective charge is Z minus S, no. So when going towards right, the Z increases by 1 unit. Z increases by 1 unit, no. When going towards right, Z increases by 1 unit. As one proton is added to the nucleus. Z increases by 1 unit. Right? And S increases by 0.35 units. When going towards right, S increases by 0.35 units. So the net effect is effective unit charge. So that will increase by 1 is increased. So minus 0.35. 1 minus 0.35. That is the net effect. 1 minus 0.35. The net effect is plus 0.65. That is what happens. When going towards right, the nuclear charges increase, then the shielding effect increase, as well as the effective charge increase. Right? So that is the idea. So you can write within brackets just write, as increasement of Z is greater than the increasement of S. That is the reason. As increasement of Z is greater than the increasement of S. That is why the effective charge increases. Right? Within brackets just write, as increasement of Z is greater than the increasement of S. Just write that thing in within brackets. As increasement of Z is greater than the increasement of S. Okay. You can put this thing as well. Right? Under that you can put this thing as well. Just write this one as well. Right? As increment of Z is greater than the increment of S, right? Just write this one as well. Z increases by 1 unit, S increases by 0.35 units. So the net effect is kind of increment by 0.65 units. Right now? That is the idea. Right. So that is all you should know about the affinity charge. Right? Okay. So you would clearly see here. You see? If you are thinking of this one, right? If you are thinking of this one, that is where we start the discussion. That is where we start the discussion, right? If you are thinking of this thing, you see, the electrons in magnesium is more strongly bound to the nucleus than the electrons in sodium. The kind of valence electron in magnesium is plus 1.65 charge from the nucleus, and which is greater than the charge felt by a valence electron in sodium, which is plus 1. So electron in magnesium, the valence electron in magnesium is plus 1.65 charge from the nucleus. That is a stronger value, greater value than the charge felt by a valence electron in sodium, which is plus 1. So that this means the valence electron in magnesium is actually greatly attracted to the nucleus. Right? This electron is actually greatly attracted to the nucleus by 1.65 units compared to this electron's attractions to the nucleus, which is plus 5 unit. So that releasing this electron is harder. Forming positive ions from magnesium is harder than the forming positive ions from sodium. That is what this says. Forming magnesium ions will be harder than forming sodium ions, as magnesium electrons are greatly bound to the nucleus, as electronic charge of magnesium is greater than the sodium's. So it is hard to release free electrons from the magnesium, so their reactivity is low. It is hard to ionize the magnesium. So if it is a harder process, it is hard to do, the reactivity is low. But here it is a simpler process than the magnesium thing. So easily this thing will happen, the reactivity is high. Right? So that is what it means. That is what the affinity charge do in these kind of reactions. So reactivity will also depends on the affinity charge of those considering elements. Right now? That is the idea. Okay, so that's it. Right now? That is all what we need to know about the affinity charge. Right? Okay. So I'll tell you another point, which will be discussed later as well, and which we will discuss at the end of the this lesson as well. Another point, that is actually basically the affinity charge is high means like this now. So if you are to consider, let's think, if you are to consider two atoms, it could be sodium and magnesium as well, right? This is your nucleus, this is your considering electron, right? If the effective charge of this thing, if you are considering the affinity charge of this thing and this thing, if the affinity charge of this thing is higher than this one, that means this electron feels much greater charge from your nucleus than this electron, right? This electron feels much greater nuclear charge right? That means that electron will greatly attracted to its nucleus than this one. The affinity charge is greater means this electron feels some greater charge of the nucleus than this one. So that this electron will greatly attracted to the nucleus than this one. So that what will happen there? So that the atom will become smaller. The valence shell will be greatly attracted to the nucleus. The valence shell will be greatly attracted to the nucleus when the affinity charge is high. That means atoms become smaller. The atom becomes smaller when the affinity charge is high. So atomic radius is another fact which will be affected by the affinity charge when it comes to same row elements, when it comes to same period elements. So when going towards right of a period, as atomic radius, as affinity charge increases, the valence shell electrons feels much greater charge from the nucleus. That means those will be attracted heavily towards the nucleus, make them a smaller species, right? So when going towards right of a period, as affinity charge increases, your atoms become smaller. As the charge felt by the electrons, the nuclear charge felt by the electrons, that is what is the affinity charge, when it increases, those electrons will greatly attracted, the valence shell electrons will be greatly attracted to the nucleus. That means those atoms become smaller. So when going towards right, the atoms become smaller, atomic radius decreases due to the increasement of the effective affinity charge. That is another effect done by the affinity charge. It affects the atomic nucleus, right, going towards right of a period, right now. So that is another usage, some application of affinity charge, the atomic radius application, right now. Okay, so that is all. Actually, that is all that you should know about the affinity charge.